This is the second hour of Physics 1C for October 25th. I just want to mention something about magnetic flux. We're not really going to use this in this chapter, although I think you might have a homework problem where you have to calculate magnetic flux, but I just wanted to say that magnetic flux is found in exactly the same way as electric flux is. So magnetic flux is found by taking... I need to zoom in just a little bit more, don't I? Yeah, I need to zoom in quite a bit more. Okay, so magnetic flux is found very similar to the way you find electric flux. All you need is to know what the size of the magnetic field is. You need to know the area through which you want to calculate the flux, and then the angle made between the area and the field vector. So, for example, you could have magnetic field lines like this, let's say, and then if you have like a surface through which you want to find the magnetic flux that has an area A, and the angle made between the two is found by taking a vector here to represent the area vector A, and then we say that these lines right here represent the magnetic field, and you say the angle between them is theta, then you can find the magnetic flux, just how we found magnetic flux in with electricity. Also, if I have a curved surface, so if I have some kind of curvy surface like this, and I've got magnetic field lines that are coming out of that, and I want to calculate what the magnetic flux is going to be. Sorry, these would be magnetic field lines now. B. Then if I have a curved surface over which I want to do this, then I have to take the dA vector for each portion of the surface, and I have to say that the magnetic flux is going to be equal to the integral of B dot dA. So it's technically a double integral, just to keep everyone happy. So this is also how magnetic flux is defined if you have a curved surface or if you have a magnetic field that changes over a region. You will be doing calculations with this, but we're not going to see the full kind of force of what magnetic flux can do until we look at electricity and magnetism combined together through what's called Faraday's law of induction. So just kind of keep this on hold for now. I'm just defining what it is so we can use it later. But one result that comes out of this is that if I take the magnetic flux over a closed surface, we learned about Gauss's law. This is what we call Gauss's law for magnetism. And in the case of electricity, when I took the flux through a closed surface, right? What did we get on the right-hand side of our equation right here? If I made this electric field and we did the surface integral of the electric field over the entire surface, what was the answer on the right-hand side? It looked like something over epsilon naught, right? What was the thing up in the top? The charge enclosed, exactly. But we learned earlier that there's no such thing as a magnetic charge, right? Which means the right-hand side of this equation has to be equal to 0. And that is one of Maxwell's equations, actually. Gauss's law for magnetism. We've now learned just two, right? Yeah. We've now learned 2 of the 4 Maxwell equations. Gauss's law for electricity, Gauss's law for magnetism. This one is often referred to as the no magnetic monopoles equation. If there were magnetic monopoles, the equation would be something like magnetic charge multiplied by something called mu naught, which we're going to learn about later. But there aren't, so sometimes this is referred to as the equation that proves that there are no magnetic monopoles or indicates that there are no magnetic monopoles in the theory. To give you an idea of why this happens, it's because all magnetic field lines form closed loops. So if I have a magnet, here, let's draw a magnet here. If I have, for example, a dipole magnet, right? The magnetic field lines for this look kind of like this. I hate drawing this so much. Magnetic field lines form these loops. Some of them might kind of like go off to infinity, but for the most part, this is what the field lines are going to look like. Some of them might kind of go like this. Okay, and the direction is from north to south, but the direction isn't really super important for what I'm about to talk about. I guess it is. The point is that because they completely form closed loops, in, out, out. If I was to draw a surface inside of here, like let's say we could call it a Gaussian surface if we want to, and I wanted to calculate the magnetic flux through that surface, okay? Oh, one important thing about this. These field lines, they actually point inside of here too. So there's also a field line from here to here. Okay. Remember that you only get flux when a field line comes in, and that's positive flux, and when the field line goes out, no, that's I got it backwards. When a field line comes in, it's negative flux. When a field line goes out, it's positive flux, right? So if you can have the same number of lines that come in as go out, that means that the net flux is 0, right? And that's pretty much all this is saying, is because the magnetic field lines are always closed loops, there's no way you can get magnetic monopoles. At least as far as we know. Maybe 100 years from now, we'll have a different idea. In order to produce these things, these magnetic monopoles, we think that we would have to produce a huge amount of energy anyway. So, all right. So, then, any questions about magnetic flux? Hopefully, it makes sense why the magnetic flux through a closed surface has to be equal to 0, because there are no magnetic monopoles. Okay. So the next thing to talk about is the motion of a charged particle in a magnetic field. And this is a problem that we're going to do, but we need to do the theory really quickly first. Oh, you know what? Before we even do this, I told you all we were going to watch a video, and then we didn't watch it. I'm sorry. We should do this. We should watch this video. It's actually really good. I don't know what I just clicked on, but whatever. Let's see. YouTube. This video is really short. It shouldn't be too hard to find. Come on. Why is this not? What's going on? Okay. Motion of a charged particle in a uniform magnetic field. There we go. Okay, I accidentally started Steam, so I'm going to try to close that out. Okay. Oh no. I was hoping that it would come right up. What if I just do magnetic force? That's it. That's all I had to do. Okay, I'm going to pause this, and I'm going to have to switch screens. Shouldn't change anything for you, but change windows. This one. Go live. I'm going to push play. If you can't hear it, say something. Otherwise, just watch along. Is the sound level okay? I can't hear it, so you can tell me if it's bad. We have this demo in the lab too. If you want me, I'll show it to you when we come back. Okay. It's okay if I stop it there? I think he's done. Okay, any questions? Mostly wanted to show you this just so you could see kind of this part right here where you're just like, got your beam. Like I said, we have the same demo at the school. In fact, you're going to do a lab with a cathode ray tube just like this, where you're going to be making a magnetic field and forcing the beam to not just curve like it is, but to curve in a circle. So, anyway. This is pretty, I mean, I don't know. What do you all think? Is that cool? Is it not cool? Is it just boring? I don't know. What do you all think? Yes, the north and the south matters, as well as the positive and negative of the charge, correct. Did you notice when he put the north in toward it, it went one way, and then he flipped the south around, and it went the other way? Yeah. You can kind of think of a, let me go back to the screen. I think so, yeah. I think that's right, Evan. The color can change depending on the gas that's inside of there. I think the one that you guys are going to do, it does look pretty blue like this. Might not quite the same color. They have it so you can really see it really well in this demo. It's a really good demo. The ones that you're going to use, you have to turn all the lights off and stuff to even see it. So, yeah. This must be a pretty powerful cathode ray tube or something like that. I don't really know. All right, so let's go back to the lecture notes and let's talk more about this. One thing that came up in that video that I want to kind of mention to help clarify some things for you are if you have, you're going to have all these problems that involve magnets and stuff, and you're going to need to know what direction the magnetic field is. You know, if we have a beam of particles like we did in this experiment, like he was showing, and that beam of particles is coming out of the page like this, so that's our velocity, right? And if I bring a dipole magnet over here, and I bring it this way, so I put the north end right here. And I know the particles that he was talking about were negative because they were electrons, but let's say that these are positively charged particles, just for clarity here. When I put a magnet in here, the reality is the magnetic field near the tip is something like this. It's kind of what the magnetic field looks like. But it's always going to be way simpler for you when you're doing your problems to just assume that if you have a dipole magnet like this, you can basically just say that the magnetic field points this way, okay? And I don't know if that helps to answer the question you had, Kavi, about the fact that the north and the south matters as well as the plus and minus, because here, can you all tell me what would the direction of the force on this particle be? If you do your V cross B, what's the direction of the force? So magnetic field's going to the right? Velocity's coming out of the page, so you do V, you gotta point your fingers back that way. You may have to like stretch your arm or something. And then you rotate towards B, which is to the left. So you go from here to here. Your thumb goes up, so the force is up, right? And then just to kind of, so I can't have much room here, but I'll just say force is up in this direction, okay? Now, if we were to switch the direction of the magnet so that we put the magnet in, so same scenario, but now just separated. If I put south first and then north here, now we think of the magnetic field as pointing this way, okay? Into the south pole, okay? And now if I have a velocity particle, a particle that's here, whoops. I have a particle that's here, and it's also going out of the page, so the velocity vector is this way. I tell you again that it is a positively charged particle. Then you can almost guess without even doing the check that the force should be down, right? But let's check just in case. So velocity vector, again, is out of the page. I need to flip my hand upside down because I'm going to rotate to B, which is back this way, and my thumb points down. So then we get magnetic force on this one is down. All right? So I hope that clarified your question about the positive, negative, and north and south mattering. When you see the north end, you should just think magnetic field pointing that way. When you see the south end, you think magnetic field pointing into it, okay? Just the same way when we talked about electric field, if I have a positively charged particle, electric field points away. Negatively charged particle, it points towards it. The north side is like the positive side, the south side is like the negative side. Okay, so that's a really good question because it hits on some details that I didn't quite hit upon. Okay, we're going to be talking about the motion of a charged particle and specifically a uniform magnetic field. And one thing I want to note about the equation before we get into this derivation. So magnetic force is equal to Q V cross B, right? So one thing I'm going to say is that because the force is always perpendicular to the velocity, okay, instead of writing perpendicular, I'm just writing this symbol right here. This symbol means perpendicular, okay? Perpendicular. Because the force is always perpendicular to the velocity, the force can't change the speed. It can only change direction of the particle. Does that make sense? If you have a force that's always perpendicular, it can never give you acceleration. I'm sorry, that's not right. That's not right. You can't increase speed. You can't increase the magnitude of your velocity. Think about that for a second and make sure that makes sense to you. There's no way a force that points down can make the velocity go up. Okay? The magnetic force is like the steering wheel in your car. Okay? The steering wheel in your car cannot change your speed. Would you all agree with that statement? There's no way you can use your steering wheel to change your speed without doing something else, like pushing the brake or pushing the gas. Your steering wheel alone can only change the direction of your speed. The magnetic force is like the steering wheel when it comes to charged particles. We can use magnetic forces to bend particles' paths, as you saw, but we cannot use magnetic forces to increase the speed of a particle. The only way to do that is to use the electric force. Is that clear to everyone? I was like, to me it's obvious, but I've been teaching this stuff for years, so I already knew it was true, and the real question is, does it make sense to you? So logically, does that make sense to you all? Well, one person said yes. I'm going to assume the other 29 of you don't understand. I know it's tricky. Think about it, understand it, internalize it, ask a question if you don't understand, but the point is that because it acts always at a right angle, it's impossible for it to do anything other than changing direction. Good, I'm glad the steering wheel thing makes sense to you. Okay, so that's literally what we use magnetic fields for in particle physics, is we use it to steer particles around and force them into a certain location so we can make them collide with each other. So, what? I said change twice? The force can't change speed, it can only change direction? Yeah, but it's two different things, right? The force can change speed. I don't know how to say it without using change twice. I'm not going to focus too much on this. Okay, so let's get into looking at some of the math of what's going on here. It's okay, my grammar's really bad, and I know I'm not really clear about explaining things. It's just the nature of being a physicist, I think, sometimes. I don't know. Alright, suppose that I have a magnetic field that looks like this. Okay? I've got a really wide range of space over which there's a magnetic field, and it points into the page. Okay? And now I say, suppose that I place a charged particle in here. Okay? And I'm going to give the particle a velocity that's in the plane of the page. Right here. So that's the direction of the velocity of the particle. Can you all tell me, think about it, and quickly answer, what's the direction of the force on this particle if it's a positively charged particle? Use your right hand rule, point your fingers in the direction of the velocity, rotate to the direction of the magnetic field, which is into the page. What direction is your thumb point? It's either going to be up or down. Points up. So that's the direction of the force, right? Now, if I'm a particle, and I feel a force like that, that's going to force me to move along a trajectory like this, basically. Okay? It's basically a central force if you think about it. And the direction of the force is always going to point to the left of the path. Okay? When I get to this location right here, the force is going to point this way. Because now my velocity vector is this way. Why did I call it VV? It should just be V. Anyway, so when I get to this position, my velocity vector points like that. And now my force, V cross B, is in like this. And we can continue this process until we get somewhere like right here, where now the velocity of the particle is this way, and again, the direction of the force is still towards the center. And then eventually it's going to get to like here, and eventually it's going to get back to its original location, okay? The particle is going to end up traveling along a circular path. It undergoes what we call uniform circular motion that you've learned about in your Physics 1A class, and it's going to be literally perfectly circular with a radius r. So the motion of a charged particle in a magnetic field, if its velocity is exactly perpendicular to the magnetic field, then it's going to produce a circular motion. And we can go back to Physics 1A and say that the net force acting on this particle should be equal to its mass times its acceleration. And in this case, we're going to be talking about the net force acting in the radial direction. So we're going to want the radial acceleration of the particle. Does anybody... Yeah, centripetal. Exactly. The force here is going to act as a centripetal force. Exactly. The magnetic force is going to act as a centripetal force. That's exactly right, Tomqui. So the acceleration in this case then needs to be centripetal acceleration, right? Which we know is mv squared divided by r. What we also know is the force acting on this particle is the magnetic force, which we've learned previously is equal to qvb, right? In this case, the velocity of the particle and the magnetic field are at right angles to each other, so I can just write this as qvb instead of qvb times the sine of 90. Although I say that, and I realize that I really shouldn't skip steps. This is an introductory class, I shouldn't be doing that. This is times sine of 90. And that 90 degrees is because V is this way, magnetic field is this way. The angle that shows up here is the angle between V and B. In this case, that's 90 degrees. So this is equal to m times v squared divided by r. What I'm going to do is I'm going to solve this for the radius, and then we're going to look at the angular speed. So if we solve this for the radius, what we end up noticing is that one of the velocities here is going to cancel. And we find that the radius of the motion is going to be equal to the momentum, m times v, divided by the charge of the particle, multiplied by the magnetic field. And that is going to be the radius for a particle that's undergoing circular motion. Oh, sorry, for a particle, if you give a particle that has a charge, a velocity, and a magnetic field, this is the type of path that it's going to take. Okay. I find that to be pretty cool. And it means that you can actually use magnets to kind of bottle and hold charged particles so that they don't actually touch the surface of a container or something like that. All right. Now, we can also talk about the angular speed, okay? If you remember from Physics 1A, angular speed is found by taking velocity and dividing by radius, okay? So if we take the velocity from our equation here, and we divide by radius, or if we just rearrange it to get v over r, what we're going to get is that you get qb divided by m, I believe, is going to be equal to the angular speed. I'll let you verify that for yourself. Just solve for v over r here, and you'll see that omega, this is the angular frequency of the motion. Now, what's missing from this? Well, the r is missing, right? The r is no longer there, okay? What this implies is I could have another particle, right, out here. And it could have some velocity v. And that velocity would probably need to be a little bit greater than this one if it wants to go on a bigger circular path. But let's assume that the particle has exactly the same charge as this one. It has exactly the same mass as this one. And let's say both of them start at the same location right here, with one of them having like a slightly bigger velocity than the other one. And then what would happen is that this outer particle would also trace around here with a circular path. The path would be bigger because v is bigger. And if you look at the radius equation, when the velocity increases, the radius increases. But the thing is that these particles would be at the same location at the same times. That's what this says, right? The angular speed is only dependent upon charge, magnetic field, and mass. So all of these particles, suppose we had a bunch of particles and we put them in this magnetic field, they'd all be going around in a circle with the same frequency, which I think is pretty cool. Some of them would go faster because they're farther out, but nonetheless, proportional, yeah, like I guess you could say that they're proportional to each other, sure. Their velocities are proportional to the radii. Anyway, but let's look at this equation. So what does it tell us? It tells us that The radius of the path that the particle takes depends on mass, velocity, charge, and magnetic field. Let's see if this makes any sense right here. Can anyone explain to me why it's the case that the radius of the path would grow bigger if the velocity was bigger? Why would the radius of the path be bigger if the velocity was bigger? And it's not that simple. Why would the radius be bigger if the velocity was bigger? Yes, that's right, Cayenne. It is harder to change the path if it's going faster. So it's going to go farther before it starts to turn in, right? Okay, that makes sense. Why would the radius be smaller if the magnetic field gets bigger? This says that if the magnetic field gets bigger, the radius gets tighter, right? Smaller radius means it's going to be a tighter circle. Does that seem reasonable? Should. If we make B bigger, what happens to the magnetic force? It gets bigger, right? If the magnetic force gets bigger, then the circle is going to be smaller. Okay. Also, if you make Q bigger, that likewise makes the magnetic force bigger as well, which then makes the size of the circle smaller, which means it's going to have more curvature. Okay. Like I was saying earlier, suppose that I have an experiment where I know that the magnetic field points into the page everywhere. Okay. So I know that we have a magnetic field that points into the page everywhere, right? And I look at some particles that are passing through here, okay? And let's say one particle does a straight line. Let's say another particle does something like this. Yet another particle starts from the same location here, but seems to curve even harder. And then over on this side, let's say that I have a particle that comes in on this side and just kind of curves out like that. Okay? So I've got a bunch of different particles right here, and I'm going to label them particle A, particle B, particle C, and particle D. Actually, let's use a different color so it stands out against that. What do I just do there? Let's use red. Well, that's fine, I guess. So let's say this is particle A, this is particle B, this is particle C, this is particle D. All right. And let's say that we know they all have the same mass, okay? Can you all tell me what the charges on all the particles are? In fact, we're going to have to say same mass and same velocity. Just to be clear here, okay? So same mass and same velocity for all the particles here, all right? Can you rank the charges of the particles from most positive to least negative? Does that make sense? So we want to rank charge from most positive to least negative. This was a problem on one of my exams I gave in the past. Or something of this form. So rank the charge on the particles from most positive to least negative. Y'all want to think about that and try to answer it? Oh, I should say most, sorry. It should be most positive to most negative, otherwise that doesn't make sense. Just basically from high to low. Feel free to just put an answer in the chat. The green lines are the paths of the particles. Okay, so each of those green lines represents the path of a particle. The magnetic field's pointing into the page with the purple lines. I should have made that more clear. These like magnetic fields pointing into the page. And we just want to figure out, rank the charges from the most positive to the most negative. Okay, so Josh, you're saying that A and B are both positive, and you know that because if I take my finger and I point in the direction of their velocity vector at any point here, like let's say I start right there, the velocity vector is this way, the magnetic field's into the page, that's going to be a force that points to the left, the particle is curving to the left, right? But we notice that particle A, which supposedly has the same mass as particle B, and the same velocity as particle B, is curving more. So that's why you're saying that A has to have a bigger charge, right? Because if the magnetic field, the mass, and the velocity are all the same, then the only thing that could be making it curve more is the charge, right? So that's exactly right. So it is, in fact, A is greater than B is greater than C. This one is, what's the charge on C? What's the charge on C going to be? Yeah, charge on C is 0, and the charge on D is negative. And these two are positive. In fact, we wanted to assign some numbers to them. We might say that this one is +2, this one is +1, this one's -1, and this one's 0, or something like that. I don't know if it's exactly +2 or +1. Not important, but we could say something like that if we wanted to quantify it. Okay? All right. A little conceptual thought to kind of think about. So now what we want to do is we want to do this problem right here. Boy, we're not going to get to all. We are going to get to all this stuff today, actually, I think, but I don't think that we're going to be doing it right now. So let's grab all of these. The ones that I want to keep here that we are going to do next are this one and this one. And these two we can move way down here. Should be enough room. Okay, let's do this problem right here. Really easy one to use what we just talked about. So to summarize the result we got, it's that the radius of the path is going to be mv over qb, right? In this problem, we have a proton moving in a circular orbit with a radius of 14 centimeters. So here's our proton. It's moving in an orbit that's circular, and it has a radius r, where the radius is 0.14 meters. It's placed into a magnetic field with a magnetic field strength of 0.35 Tesla. It tells us that it's perpendicular to the velocity of the proton. Okay, so that makes it pretty easy to see that if the velocity of our proton is like this, then the magnetic field needs to point into the page. We'll draw that on here. So here's our magnetic field lines pointing into the page. So there's B. And all we want to do is basically just use this equation to find the radius of the path. Pretty easy to do. We just need to know what the mass of the proton is. The mass of a proton is 1.67. This is obviously something you can look up. 10 to the negative 27 kilograms. And then we also need to know the charge on the proton, which is 1.6 times 10 to the minus 19 coulombs. Putting those together, we can see that the radius of the path is going to be multiplied by velocity. Oh, we're trying to find velocity. My bad. So we want to solve this for v, so we're going to get that v is going to be equal to qbr divided by m. So we're going to have velocity is equal to that times magnetic field, which is 0.35 Tesla, multiplied by the radius of the path, which is 0.14 meters, and divide by mass. And throw this into a calculator. So we have looks like about 4.7 million. 1, 2, 3. 4.7 million. And if that seems like a big number, it's a small particle. Small particles move really fast. It's just how it works. Okay. Yeah, any questions about that? Pretty easy plug and chug, but we're going to do one that's a little trickier next. because the force has to point to the center. And the only way that's going to happen is if... you can work it out for yourself using the right-hand rule now. So I was kind of like working backwards. I knew I wanted it to curve left, so I picked the velocity this way. And you can actually... I was also just thinking about, and just like at my picture from before right here, right? If it wants to go in this type of direction, I know that when it gets to this position, it's going to be going down, right? So that's also how. Okay. I could have chosen the velocity to go the other way, by the way. Like, if I had picked, for example, if I had chosen the velocity to go back this way, for example, all that would have changed is my curve would have been like this. Does that make sense? Because if I switch the direction of the velocity, it switches the direction of the force so that it's going that way now, and then it would curve around like that. So really just up to you to figure out how you're going to draw it like that. Good question, though. Okay, now, this is a special case. This is a proton moving perpendicular to a uniform magnetic field. Okay, it's a special case, and so is what we derived right here. But we can apply what we derived to a situation like this. So I'm going to take some time to look at this picture here because I think it can be quite challenging to understand what's going on here. So this is the general case of a charged particle moving in a uniform magnetic field B. The magnetic field does no work on the particle, so its speed and kinetic energy remain constant. Now the difference here is that our magnetic field is now aligned along the x-axis, okay? You can see the y-axis points up and the z-axis comes this way. And now what happens is that when our particle is placed into this magnetic field, it no longer has its velocity exactly perpendicular to the field. It now has its velocity kind of at an angle, okay? So if its velocity was straight up and down, for example, it would have just gone in a circle like this and stayed in one location, okay? But if you take that motion of something moving in a circle, right, like this, and you add to it an additional component of velocity that points along the x-axis, what's going to happen is it's going to start to move over a helical path like this right here, okay? So the combination of something moving in a circle combined with something moving in a straight line is going to construct a path that's like a helix, basically. So take a moment for yourself and see if you can understand that based on the picture here. This particle has a velocity vector that's not just this way, but it also has a component this way, which means it's going to go in a circle, but it's also going to kind of translate to the right. Okay. Does that make sense? Can you visualize it? You have to really kind of... yes. Well, for the most part, yes, Justin. Yeah. There are going to be special times in its motion when it only has 2, but in general it will have 3. Yeah. Yep. Yep. Can you all picture it in your mind? You take something that's moving like this, right? And you give it a push. So you push it this way. So when it's at the top of one of its trajectories, you come in here and you're like, I'm going to give it a push this way. So now it doesn't just go in a straight line. It kind of does this, right? You could push it back the other way and it would go like this. Hopefully you can visualize that. We're going to do some calculations with it, and I hope that helps you to see what's happening here. All right, let's go through this. So here's a problem where we're going to look at exactly something moving like this. I'm going to mention one other thing that I didn't say, which is that this equation right here, okay, the R equal to m times v divided by qb, it is very specific to the derivation that I just did. And in reality, what you care about is the component of the velocity that is perpendicular to the magnetic field, okay? So what does the S symbol mean? Oh, right here? That's the symbol your book likes to use when they break things up to components. I don't know why they do that, but they do. They're like, hey, we're gonna break into components, we're gonna draw this S on here. Go back and look at the stuff in Physics 1A, they did the same thing. It's all over the place. I don't know why they do that, but never seen it, eh? Okay, anyway, so right, so this equation, r equal to mv over qb, the velocity that we care about here specifically is the component of the velocity that is perpendicular to the magnetic field. Okay, so v perpendicular is going to be the component of the velocity that is perpendicular to the magnetic fields. Okay, so let's do this problem now. I'll leave the picture up here so we have it as reference. I'll blow the problem up. There's a lot of words in it. Okay. So this is in a situation like that shown in 27.18. The charged particle is a proton, again, giving these values. And the uniform 0.5 Tesla magnetic field is directed along the x-axis. So we could say that B is equal to 0.5 Tesla times I hat. At t equal to 0, the proton has velocity components Vx equal to 1.5 times 10 to the 5th meters per second, Vy equal to 0, and Vz equal to 2 times 10 to the 5th meters per second, right? So we can actually write our velocity as a vector now. This is actually a vector too. It has components of 1.5 I hat plus 0 j hat, which you don't really need to write, but I'll write it anyway, plus 2 k hat, and then all of that is times 10 to the 5 meters per second. Okay. Now, it says only the magnetic force acts on the proton. Part A says, at t equal to 0, find the force on the proton and its acceleration. And then B, find the radius of the resulting helical path, the angular speed of the proton, and the pitch of the helix, which is the distance traveled along the helix per axis of revolution. So that's actually going to be from here to here. I'm going to call it delta x. This is going to be what they call the pitch. But that's the last thing we're going to calculate, so let's not worry about that for now. Part A. Let's do that first. It says, at t equal to 0, where the velocity has the components Vx equal to this, Vy equal to 0, and Vz equal to this, we want to calculate the force on the proton and its acceleration. Okay, so we want to find force on the proton, which is going to be magnetic force, and we want to find acceleration. Okay? Oh, we got to take a break. Let's finish this problem, then we'll take a break. Okay. So, to find the force, given these values, we can use our QV cross B equation. Okay, so we can do FB is equal to QV cross B. Now, one thing to ask is, are these values consistent with the picture? With 1.5 I hat as the velocity and in the x direction, and 2 k hat being the velocity in the z direction? I mean, we can imagine that 1.5 is the velocity in the x direction, right? But it looks like the velocity vector here is pointing this way, which is like negative z, positive y direction, right? So I don't want you to think that these numbers correspond to the picture, but they do correspond to a point on the picture, which I think is down here. I'll draw it on this point because it's probably the clearest point that I can draw. If we have a positive z component and a positive x component, I think this is our velocity vector here. That's the velocity vector for the part that we're looking at. Anyway, not important unless you're confused, but all right, let's start calculating this. So this should be equal to Q, which is 1.6 times 10 to the minus 19. And then we have to do V cross B. So V is this. And we have to cross product that with the magnetic fields. Right? And this calculation is actually very, very simple because we know that if we do I cross I, we get 0. Can you all tell me what do you get if you do K cross I? What is K cross I? It's J. Okay, so again, we're looking at the particle when it's down here, right? And we've just figured out that the force on the particle points toward the center, which is good. Right? That's a good sign, right? Because if the velocity is out and the force is up, we can imagine that it would curl into the page, right? It would curl back up that way. And if you do 1.6 times 2 times 0.5, we don't need to do I hat cross I hat, right? Because it's 0. Then we get 1.6 times 2 divided by a half, which is going to be 1. And then 10 to the negative 19 times 10 to the 5 is 10 to the negative 14. So this is 10 to the negative 14. And I'll erase this. Apparently not. I will erase this, and I'll write it as a 4. All right. So that's our force, and acceleration is very easy to find from that. Acceleration is just going to be equal to the force divided by the mass. So that's going to be equal to that number divided by the mass of the particle, which is right here. In the interest of saving time, I'm just going to plug these things into this calculator here. So if we take... All right, seriously, I got to pull this back up. Push this button. I got to go over here. So we want to do force over mass. So if we take the force we got, which is 1.6 times 10 to the minus 14, and divide by the mass, which is 1.67 times 10 to the minus 27, we get 9.6 times 10 to the 12, which seems like a really huge acceleration. Okay, so that's our acceleration there. Those are the answers to part A. Hopefully there's no questions about that. If there are, save them for the break. Part B, find the radius of the resulting helical path, the angular speed, and the pitch. Well, the first two we can do relatively easily by using some equations. First of all, we can use this equation here to find the radius of the path. We just need to find the component of the velocity that is perpendicular to the magnetic field. In this case, I would say, if you think about the z component of the velocity, it's going to be perpendicular to the magnetic field guaranteed, right? This component right here is going to be v perpendicular. This component here is going to be parallel to the magnetic field because it's I hat, and magnetic field's also I hat, so they both point in the positive x direction. But k hat is guaranteed to be perpendicular to I hat, right? Now, if our particle also had a velocity here, a velocity component here, like if this was, let's say, 2 or 3 or something like that, we would have had to vector sum these two because both of them would be perpendicular, right? But in this case, we don't have to do that. We just have to use this one here, but just something to keep in mind. If we also had a j hat component, it would also be perpendicular, and we'd have to vector sum these to get v perpendicular, okay? So in reality, v perpendicular in this particular problem would come from these two, but we don't have to worry about that because this is 0, right? Okay, so putting everything together, we have mass is 1.67 times 10 to the minus 27 kilograms. Perpendicular velocity is going to be 2 times 10 to the 5 meters per second. We're dividing that by q, which is 1.6 times 10 to the minus 19. And we multiply that by b, which is 0.5 Tesla. Okay, we throw that all into a calculator. Which this time I'm not going to do F11. And I push this. And now we plug into this calculator, so we've got times 2e5 divided by 1.6 e minus 19 divided by 0.5. And we get 4.17 times 10 to the minus 3. That is the radius of the motion. I didn't write it down. 4.175 times 10 to the minus 3. About half a centimeter, or about 4 millimeters, basically, right? So the radius of the helical path, so that's going to be this radius, r, is going to be about 4 millimeters. Okay. So anyone have any questions about that? We also want to find the angular speed of the proton. For that, we have an equation that says that the angular speed is independent of the velocity, and it's equal to QB times R divided by M. Is that what it is? Omega equal to just QB over M. Sorry, there's no R. I didn't think there was an R. Just QB over M. So that's easy enough to calculate. Q is 1.6 times 10 to the minus 19 coulombs. The mass is 1.67 times 10 to the minus 19 coulombs. And we're multiplying that times the magnitude of the magnetic field, which is 0.5 Tesla. So we're going to get, so it's QB over M. Did I do that right? 1.6 divided by 1.67 times 0.5. Okay, we get 4.79 times 10 to the 7. We're going to need this for the next part. So this is about 4.8 times 10 to the 7. It's radians per second. That's how we measure omega. So that's the angular speed. Next, we want to find, so that's basically the rate. It undergoes 4.8 times 10 to the 7 radians per second. We could also convert that to cycles per second if we want to, because if we divide that by 2 pi, we're going to get an answer that's something like 8 times 10 to the 6th, which would be 8 million. So this thing undergoes 8 million cycles per second. That means one cycle is one loop, right? This particle undergoes about 8 million loops every second, which is really fast, right? If you think about it, it goes like that 8 million times every second. That's insane, right? Okay, just to give some understanding of what this means. Okay. Oh, there's an issue here. That's supposed to be 27. I was writing super fast. In case you're wondering why you don't get the same number, that's a 27. Okay, so next we want to, this is kind of the tricky part of the problem, and I know you have a homework problem about this, so that's why I want to make sure I cover this today. Next we want to find the pitch of the helix, okay? This is the distance traveled along the helix per axis of revolution, okay? That's to say how far apart are is it a spring that's like kind of like really compressed, or is it a spring that's stretched out, right? How far apart are the individual little rings right here? So that's what I called delta x, the pitch, okay? So delta x then should be equal to, I don't know, what's it equal to? How do we figure it out? We know the particle is traveling in this direction with a constant x velocity, right? We said before that the magnetic field, all it can do is change the direction of motion. It cannot change the speed of the particle. So we know that this is a constant for the particle, right? And in general, just to take you back to physics 1a, we know that if something moves with a constant velocity, vx, that if we multiply by the time that it takes to complete the loop that we're talking about, one loop, then we can figure out exactly how far it moves. And we know this one. So we just have to think about how are we going to calculate this. T is going to represent, in fact, I'll use the symbol that we've used in the past. Maybe it'll make it easier for you to figure out what the answer is. I'm going to use a capital T. So T is going to be the time for one revolution. Does anyone remember how you calculate that? If I have a particle that's moving in a circle, and I know at the rate at which it's moving, the angular speed, how do I calculate the time that it takes for one revolution? Two pi divided by omega, that's right. T is equal to 2 pi. 2 pi radians in one revolution divided by omega. Because omega is radians per second, 2 pi radians per revolution, this gives you seconds per revolution. Okay, so if we do that and put it all together, we're going to get that the pitch is going to be equal to the x velocity, which is this, 1.5 times 10 to the 5th meters per second. And then the time for one revolution is going to be 2 pi divided by if you're worried about the units, this is on the numerator, it's basically 2 pi radians per revolution. If you look at the way things cancel out here, radians, seconds, you're going to end up with just meters. Meters per revolution is what you're going to get as your answer. And plugging everything in together here, then we're going to get, let's push F11, go back to here, move it over here. So we have 2 times pi times 1.5 E5 divided by 4.8 E 7. I guess we could use the number that's above there. That's fine. So we get about 0.2. So it's, what is that, 0.2 millimeters or about 2 centimeters? I'm just going to write that the answer is 2 centimeters. So you get that delta x is about 2 centimeters. Okay. So nice, simple answer. Little tiny circle, right? The circle is really tiny, 4 millimeters, right? But the distance that it moves is 2 centimeters. So it's kind of like a really tiny circle that's stretched out, right? If we were to draw a picture of what we just saw, or what we just calculated, it would be something like this. It would be a really tiny circle that has really long distances between it, okay? Okay, we gotta take a break. It's 3:30, so we'll take a break until 4:41, and we'll have about 40 minutes left for class. All right?